Okay, good afternoon, everyone. So last time we derived an important equation, which was the bias variance decomposition. So basically, this is what it is here. And this tells us that the mean squared error in our estimate y hat is equal to this irreducible error component, which is basically the noise variance in the targets, plus the expected squared bias, plus the expected variance. The squared bias, or the bias, tells us how far the average estimate is away from the truth. So in these kind of cartoons here, the average estimate would be in the center of that cluster. The truth is here. You can see that they're different, so this would be a biased case. Over here, the average estimate is right at the truth, so that's unbiased. But then the variance measures the distance between the average estimate and the typical estimate. So basically, it's the variance is the average squared deviation of something from its mean. So in this case, here, this is also unbiased in that the average is here, but you can see the samples are a lot farther from their average, which means that they have a higher variance. So when we look at the mean squared error, we can think of it in these three individual terms. And when we design machine learning approaches, we often see that we face a trade-off between these second two terms. So if we make our model too simple, then the bias goes up. If we make our model too complex, then the variance goes up. And so we want to find a model complexity that is in between so that the mean squared error is minimized. So that's what we did last time. We went through this long derivation here, but I think part of what came out of that is a bit more comfort in dealing with expectation and the independence and linearity properties, which show up over and over again. Okay, and then we saw this example where we saw the bias and the variance shown by these little error bars. Okay, so what I want to talk about today is just a few more things in this note packet. So if we look at the special case of linear regression, then we can actually go a little bit further, and we can say some more specific things. Okay, so in the last lecture, this was our model for what happens at an ith training example. We have some function operating on the ith training features and then plus some noise. But what we're saying here with linear regression, the function is just this linear function that we studied in Unit 2. And so it's not polynomial, it's just linear, and that linearity will help us to do the analysis. So we have some sort of true number of coefficients here, a true model order. And then we have our regression model. A regression model is going to look similar. It's also going to be linear, but the value of D might be different than the truth. So we'd like to know, how do things change when D is different than the truth? Also, we'd like to know the dependence on the number of training samples in our data set. Okay, so there's a packet down here is the link, and it derives three main results. The first result is that if you don't have enough training data, in other words, if the number of training samples is less than the number of features plus 1, you're in trouble because the matrix A transpose A that you use to compute the least squares weights beta hat, that matrix is not invertible, so you can't really uniquely compute those weights. So it's not exactly clear what the least squares solution is. Basically, there's a whole bunch of different beta hats that will all give you the same least squares solution, but they might behave differently in a test scenario. So that's the first result. If you have too little data, it's not clear what the least squares solution is. Let's assume we're not in that situation and we have enough data. So maybe I'll stick this condition and the second result, even though it holds more generally. So let's just assume that we do have enough training data. We can get our unique beta hat. We have a least squares solution. So now, if your assumed model order is less than the true model order, you can prove that your estimates will be biased. So that's not surprising, right? If you select D less than D true, you get biased. You don't find a y hat that is equal to the true y on average. You get a systematic error. Okay, then the next result is if you have enough training data and your model order is at the correct one or larger, turns out that you get unbiased estimates. And again, just to remind us, bias, the bias on y hat that written as a function of x is this conditional expectation. So for a fixed x, it's the average difference between the prediction y hat and the true y. So this goes to 0 whenever you choose D equal or greater to the true model order in this linear case here. And the third result is maybe the most interesting. So this result, the derivation needs a bit more assumptions, not too many more. You have to assume that you have a lot of training samples in order to do some stuff in the derivation. And here we'll assume again that we're in this unbiased situation. And we'll also assume that the test features have the same distribution as the training features. So in this case, what's interesting is you can actually write down an exact expression for the variance, and it's D plus 1 divided by n times sigma squared. So what's remarkable about this expression is it shows exactly the penalty for choosing too many coefficients. So the larger D is, the larger the variance is, right? Grows linearly. Second, it shows the value in having a large training set. So the larger your training set is, the smaller your variance gets. This is some hint of why we like large training sets in machine learning. And finally, you see that everything is affected by the amount of noise in those targets. Everything is scaled by that. Okay, so that's something that we can say specifically with linear regression, least squares linear regression. But otherwise, analyses like these are a lot harder. And we can take a peek at the handout, but basically it's just using expectation with linearity and the independence assumptions. So if you want to look through that, it has a lot of good sort of practice examples of how to do that stuff. Okay, any questions on this slide? All right. And one more thing to talk about. Let's talk about the sample estimators that we introduced way back in Unit 1. So remember that we had this idea of the sample mean. So if you have a bunch of numbers, Zi, and you want to know the sample mean, you just add them up and divide by the number in the list. We call that Z bar. Right? So now that we have a bit more understanding of random variables and so on, we can actually analyze how good of an estimate this is. So here's the situation. Imagine that we have a random variable, capital Z, and there's a true statistical mean, mu. So let me give you an example. Let's say I have a coin. The coin is either 0 or 1, heads or tails. And somebody is trying to convince me that this coin is not fair. So they're saying that it has a particular mean mu that's different from 0.5. So the question is, can we verify that or not? Okay, so we also need to know the variance on that random variable z. We'll call that v. So, okay, so what we're going to do is we're going to test whether there's a bias coin or not, we're going to flip it n times, and we're going to average the results, and we're going to get finally z bar, right? It's going to be some number between 0 or 1, and it's going to be an estimate of, the flipping probability of that coin. Let's say if maybe 0 is heads, 1 is tails, then mu is the true probability of heads. Okay, so we flip it n times. Are we going to get exactly mu when we average those flips? No, right? What happens if I take the number of flips to infinity? Does that sound familiar? If I flip this an infinite number of times and average it, what will happen then? Does anybody know what that's called? It's called the law of large numbers. It says that when you do this sample mean, as n goes to infinity, this actually becomes perfect. But let's not assume that. Let's try to explain why that happens. Okay, so if I did this experiment just once, in that case, we could think of these zi's as just numbers, sequence of zeros and ones. But I want to understand what happens in general if I do this experiment over and over again, or if I just do this experiment tomorrow. I want to predict what's going to happen when I do that experiment. So I can't really think of these zi's as just raw numbers. I actually want to think of them as random variables too. So what I'm going to do is I'm going to assume that each of these zi's is an independent copy of this random variable z. So each of these zi's is going to have a statistical mean of mu, statistical variance of v. And they'll all be independent. So that's going to be my assumption. So I'll write here. So assume independent, identically distributed random variables. So now, when I compute this sample mean, if I think of these zi's as random, then even the mean z bar becomes random, right? And then I can understand how good is that sample mean on average, and how far does it deviate from its average? What's its variance? And that will help me analyze how good of an estimator this sample mean is. Okay, so what we can do, maybe we'll take a peek at this in a moment, but in this handout, there's a short derivation that first shows that the expectation of the sample mean is mu, which means that on average, when you do this, you get the right number, the correct number. So we call that an unbiased estimate. So this z bar is an unbiased estimate of this true underlying mean mu. So that's really great. And that's sort of an explanation for why people use this so much. It's simple, it's correct on average, very common. Okay, so that's one important result. Z bar is unbiased. But now, as we know, z bar is almost never in any experiment will z bar exactly equal mu. It's always going to be a bit off. On average, it's sometimes greater, sometimes less. On average is correct, but in any given experiment, it's going to be off. So how far does it deviate from its average? That's exactly what the variance tells us. Right, so we're looking at the average of z bar. So how far is z bar away from its average? You square that and you take the statistical average of that. It turns out the number you get is v over n. V is the variance, n is the number of times you flipped it. flip the coin. So what does this tell us about number of coin flips? What happens as I do more and more flips? Variance decreases, right? So now you can see why this law of large numbers, as we take n to infinity, what happens to the variance? It goes to 0. So if you could flip it an infinite number of times, you could figure out exactly what mu is. Now in practice, we can't flip it a million or an infinite number of times, so we have to stop somewhere. Wherever we stop, this is useful to tell us how precise our estimate of the average is. You guys have actually all seen this in the previous unit. This is just the standard error squared because it's a variance. If you take the square root of this, it's the standard error. So this is the explanation for where that standard error equation comes from. So this is standard error quantity squared. Okay, so when we take the square root, you can see we're going to get the standard deviation divided by the square root of the number of terms in the average. That's the standard error. So when we were doing k-fold cross-validation, we saw this. In that case, n was k, and we were asking the question, like, how much should I trust the validation errors coming out of my k-fold cross-validation? And we saw that you could try to estimate their standard deviation. So for that, we don't know the true variance. So even for this, we have to use an estimate of it. But then you divide by the square root of the number of things in the average, and that gives the standard error. Okay. All right, so this is super important stuff. Summarized here in a few lines. I'm pretty sure you've seen this way back sometime in a probability class, but are there any questions on these ideas? Is this making sense? Kind of? Okay, so let's switch gears. Let's say my goal is not to estimate mu from a number of realizations of the random variable, but my goal is to actually estimate v. So one application we just saw of this is when I'm doing k-fold cross-validation and I want to measure this thing. I don't know v, so I actually have to estimate it from the data itself. So to do that, we have our sample variance, which we saw back in Unit 1, and it says to first compute your sample mean, then to look for how much variation you have in zi around that sample mean using this expression. And in this expression, you divide by the number of samples. And previously we said that that was the unbiased version, and now we understand a bit more about what we mean by that. So in particular, sorry, that was the biased version. This is the biased version. So this is what happens. So this is going to be a random variable, right? Because we said that these guys are all random. So this is just another random variable. So if you go through the analysis and you look at what is the average value of this random variable, you find that it's n minus 1 divided by n times v. So for any finite v, this is a little bit less than the true, for any finite n, this is a little bit less than the true v. So it's not telling you the variance, it's telling you something a little bit smaller. So this is a biased estimate of the variance. Okay. But if you really care about that bias and you want to remove it, it's easy to do. You just come up with an estimator that instead of using n here, it uses n minus 1. And if you do the analysis where you look at the expectation of this quantity, you find that it exactly equals v. So this one is exactly, it's correct on average. Now that doesn't mean that every time you compute this that it is equal to v, it just means on average it equals v. Every time you compute it, it's probably going to have some sort of error. Okay, so are we clear so far on these things?
Actually, I was not able to figure out how we went to step 3 from step 2.
So, oh, okay. So, I mean, I guess you can sort of see it like this. You can see that this value is going to be linearly dependent on any scaling I apply to this. Right, so let's say I multiply SEZ by 2, then expectation of SEZ also gets multiplied by 2. So let's say that I essentially want to cancel this. So I want to multiply SCZ by the inverse of this, which is n divided by n minus 1. And if I multiply that times this, I get 1 over n minus 1. So that's why we use this, and why it leads to just V alone, the expectation. Okay, any other questions? Okay, so then at this point, we have two different choices for how we can compute the sample variance. We can do this biased version, or we can do this unbiased version. So you might wonder, well, which one should I choose? And there's no perfect answer to this. It really depends on what you want. So if you really care to not have any bias, then you definitely want to use the unbiased one. But what if you said, I don't really care so much about bias. I want this thing to be as close to the truth as possible on average. And so you have to come up with sort of a way to describe that. So if you said, okay, what about the mean squared error? The mean squared error is this quantity for SEZ. So you take the estimate, you subtract the truth, that's the error, and you just look at the average squared error, the mean squared error. Right? That is the mean squared error for SEZ. Similarly, we have over on the right the mean squared error for Xi ZZ. And you can do an analysis of this. Again, it's not too bad. And you can compute expressions for both of these. And when you compare them, you actually find that the biased one has a lower mean squared error than the unbiased one. So if you really care about mean squared error, you actually want to use this biased one. If you care about it being unbiased, you want to use the unbiased one. Different applications have different demands, and so people make different choices depending on the application. But what we see here is we see another example of the bias variance trade-off. Not exactly with complexity in terms of model order or something like, but just with the scaling. So just by scaling this estimator to here, you can see you can go from a situation where you are sort of, let's say, over here. So this is, if you want to minimize the mean squared error, you accept some bias. If you really don't want bias, then your mean squared error is larger, but your bias is smaller. So it's, again, bias variance trade-off. Okay, there's a question?
How are we so sure that, like, when we divide it by n minus 1 over n, so, like, that, what is the intuition behind that? Like, how will the biasness will remove from that?
I guess one way to do it is just to take this expression and do the analysis, take the expectation, you do that and V comes out. So if you didn't have the intuition as to how to make it unbiased, that's okay. It's, for our purposes, it's just enough to be able to do the analysis and to see that it comes out unbiased. Okay. And we can take a look at the analysis in just a moment, but before we do that, just want to see, are there any questions so far or anything? Yes?
With enough, with big enough n, do those become sort of negligent?
Yeah, with a big enough n, you can see that these numbers here, they both get very close to, well, actually, they get small. But you no matter what n is, you always have this relationship. So for any n, this one is worse than this one. All right. So let's just take a quick peek. Why isn't this working? Okay. so this is the derivation here. I'm just going to try to convince you it's really not too bad. So here I'm using, so unfortunately my pen doesn't work anymore. So although in the notes we use a little n here, I'm using a capital N, but otherwise, yeah, it's just, here's a few little things to notice. So these are kind of interesting expressions. So the first one, that's just, if xi are these random variables with the mean mu, then by definition that holds. Second line, we have derived before, think that the expected squared value of a random variable is its mean squared plus its variance. That's where this second line comes from. And the third one is sort of almost a combination of the first two. So here, I and j, you have to ask the question, are they the same or are they different? If they're the same, if j equals I, then you're back to that expression, the second one. But if they're different and they're independent, then you can realize that this is just the mean of the first times the mean of the second. They have the same mean, so that's just the squared mean, which is mu squared. Okay, so we have this variable here. This is called the Chronicler Delta. This guy is you can think of it as an index. Whenever its subscript goes to 0, it turns on. Whenever its subscript is non-zero, it turns off. So here, when I equals j, this turns on, and you get the b up there. But when I is different from j, it turns off, you just have mu squared. Okay, so this thing is very useful. It comes up in a lot of different analyses, especially when you have multiple sums. You can use this a lot. So I just want to point that out. And so if we want to look at the analysis of x bar, you can see that you just plug in the expression for x bar. That's the sample mean. Using the linearity of expectation, you can move it through to the inside, apply it to xi alone. And then we know from before that that's just mu. And you can see here, we're just averaging mu, which is the same always, so we just get mu. So that shows the unbiasedness of the sample mean estimator. So now, to analyze the sample variance estimators, they're both scalings of this quantity here. So let's just analyze this quantity without any scaling first, and then we can apply it to both later. So again, by linearity of expectation, you can move the expectation to the inside. Then you can expand that quadratic into these three terms. And then you can, again, use a linearity of expectation to look at expectation of first, minus 2 times expectation of this, plus expectation of the third. Okay, so before we saw that expectation of the first is just mu squared plus b. Now for the next one, we have to plug in the expression for x bar, which we have here. Again, we can use linearity to move the expectation and apply it just to these variables here. Plug in our expression with our Chronicler Delta before, we get this. And now, you can see the first term here is just 2 times the average of mu squared, which is just 2 mu squared. What about the second term? So if I fix I, there's only one term j in the sum that matches I, right? So there's only one time that delta comes alive. And when it does, it has a value of 1, so then we get v times 2 over n. So that's what happens when you have that delta inside a sum. Sometimes it's called the sifting property. Okay, I'm going through this because this stuff will come up on homework and maybe exams too, these same sorts of computations. Okay, so what about this term, x bar squared? So this is a little bit more involved. So we have to put in this whole average and square it. And okay, we can pull this 1 over n out of the square. It becomes 1 over n squared. right? That's where this comes from. But then I have to square this sum. So we have to be very careful here. A lot of students will write the same sum twice using the same indexing variable, and then they'll do some crazy stuff, and something wrong will come out. So really, we want to use the same sum. We want to use different indexing variables. So here I have really, this is shorthand notation for a sum over xi and another sum over xj. And so I'm really summing over all possible pairs of I and j, going from 1 to n. And I'm summing this quantity. So again, I can move the expectation to the inside, apply it only to this, and then you get this quantity. And now we have to look at this. So this is, if I'm summing over all pairs of I and j, there's n squared pairs, and there's n squared here. So this first term is just mu squared. Okay, what about this next term? That's what we get over here. So now I'm summing over all pairs I and j, but the only way that this comes alive is non-zero is when I equals j. Right? And so for that, there's only n times where I will exactly equal j. So this turns into an n, cancels one of these n's down here, and we get that. Okay. Does that last part make sense?
Can you explain real quick how the n's disappear when you go down to like the mu squared? Like, why is it not?
Why didn't I write equals 1 to n? Or
Right. So let's say your second derivation.
Because you sum the mu n times or n squared times.
is that? So are you asking about like how did this
Yes.
turn into that? Okay. So basically you can say that this is summing from j equals 1 to n. And so it's, if I just apply that to this, I'm going to get n times n mu squared.
Okay.
And then the n gets
Yes.
canceled.
Okay.
Okay, so so we have these three terms. We analyze them. We can plug them back into that earlier expression. And when we do, we get this, and then we simplify it, and we find that gives us this. And here we see that this is not equal to n times v, as we might hope. It's actually equal to n minus 1 times v. And that's when we can see why these two different sample estimators, one gives you bias, one gives you no bias. Okay. So part of why I want to show you here is that you're all capable of doing this type of derivation. You just have to go through, use your expectation identities, keep your sums straight and everything, but you're all capable of this. And it's stuff that you'll get some practice on in the homework. But it's a definitely popular type of material for exams. So important to practice it. All right. And there's a similar similar analysis of the variance, mean squared error, and so on. But all right. Okay. Any questions on anything? All right. So pretty much finishing up this unit now, so we can ask a question which will take us to the next unit. So what we have been focusing on in this unit is we've been thinking about model order selection, which is, for example, choosing among these three models. Do I use one feature? Do I use two features? Do I use three features? But someone might say, well, why am I constrained? If I use x3, that I always have to use x2 and x1. What if I just want to use x3 alone and maybe x3 and x1 and not x2? What if I want to look at maybe x2 and x3 but not x1? Could I come up with different combinations of these features? And the answer is yes. Then we're asking a different problem. It's no longer a model complexity problem. It's more like what we would call is which subset of features should I use to estimate y? Should I leave particular features out because they are hurting me more than they're helping me? Now we have an understanding for why leaving a feature in could hurt. Because maybe if this x2 is not useful, if it really has nothing to do with the target, it's not going to help you remove bias, but it is going to add to your variance. So by leaving it out of the model, you will reduce your variance without affecting your bias. So if you have, in fact, a value x it's related to y, but in a very, very minor amount, even then, you will get a little bit of bias by leaving it out, but you might have a bigger reduction in variance than an increase in bias, so you still want to leave it out. Okay, so it's not such an easy problem anymore because there's so many possibilities of which features you could leave in. How many possible subsets do you think we have? If I have D features, how many different ways are there to use them? Some function of D. Any guesses? 2 to the power D, exactly. There's 2 to the power D possible subsets. So 2 to the power D grows very quickly with D. Once you have like D equals 20, 2 to the power 20, that's a very large number. So it turns out that in principle, we can approach this problem just using cross-validation. You might say, well, just look at every possible combination of subsets, use cross-validation to see how well that will work on your test set, and then just choose the one that works best. And that is actually the optimal thing to do if D is small enough to test them all. But because D is often too big and we can't test them all, we have to come up with some more creative strategies to manage the computational complexity created by this large number of possible subsets. So that's actually what we will study in the next unit. That will be the main question, is how to do, this is called feature selection. Which features do I want to select for my prediction? So the whole next unit is on feature selection. All right, any questions before we move on? Yes.
I thought that if you had let's say beta 2 x2, if that particular feature wasn't helpful, then wouldn't your beta just be small?
You could have, yeah, that's actually a great question. Would beta be small? So let me give you an example where that might not be the case. Let's say that I had 2 features that were identical. So they're going to have the same betas whenever I fit them, right? But being identical, I don't want to include both. I could get away with, from the bias perspective, I would be just fine including one. And from the variance perspective, I would be much better off choosing one and not both. So there's an approach where you can't, it's not just enough to look at the size of the betas. Maybe we needed to think about it more deeply to figure out which ones to use. And you would, if you did this cross-validation where you tried every combination, you would see that combination where you're only using one of those 2 redundant features would be better. Okay, but you're actually right that to a large extent, just looking at the sizes of the betas can tell us a lot about which ones are more important. And we'll talk about that in the next unit. Okay, so moving on to the next unit. So again, feature selection, and we'll learn, we'll kind of focus on this approach called lasso, and we'll learn new ways to analyze things probabilistically called maximum likelihood. Okay, so just to start at the beginning, the data set we're going to be using for this unit is this Psa data set. So Psa is a chemical in your blood that you can measure. It's the most common way for males to test if they have prostate cancer. And so usually what's done is at your regular checkup or whenever you get a blood exam, they test Psa, and if they see that this is elevated, then they say you should start thinking about whether you have prostate cancer. You should get get some more testing done. So what was done in this data set was they measured the PSA level of 97 men just before they were going to get their prostates removed. So I don't exactly know. Probably a lot of them had prostate cancer. Maybe some of them didn't, but were getting their prostates removed for another reason. I don't know. But in any case, when they removed their prostates, they were able to look at them, the cells in a microscope, and they were able to do all these other measurements and so on. And they measured 8 different biometrics, including, whether if there was cancer, how large did this thing grow, what was the weight of the prostate, what's the age of the person, all this stuff. And so we would like to know whether we can predict PSA level from those other 8 biometrics. So it's a little bit backwards from what people do in practice, in the sense usually you measure PSA and you use that as a predictor for whether you have prostate cancer. But here, because we're going to formulate this as a regression problem, we're measuring all these biometrics, and we're going to use those to see if we can predict the actual level of the prostate in the blood. So this is a very popular data set used in a lot of machine learning classes. It's also used in one of the famous books, Elements of Statistical Learning by Hastie. You can download it from many websites. Again, 97 patients, 8 features, shown on the right. And the target variable is not the PSA directly, it's actually the log PSA, just because PSA can vary on such a wide, many orders of magnitude, so we're going to actually try to predict the log of the PSA. Okay, so that's the setup. It's our data set. So the first thing we're going to try is just, what we know best, least squares linear regression. So we're just going to try using all the features. And so in that case, this is our equation. These are our predicted betas that we get from least squares linear regression. We're using all 8 features. Y is the target PSA level. Y hat is our prediction. And so again, we can ask the question, why are we using linear regression? Well, it's easy. We know how to use it. But also, as was pointed out today, it's actually pretty useful. If you look at the different betas after the fit, you can get an indication, not perfect, but some rough indication of how important that feature is in predicting Y. We have to be a little careful here because this is not true unless the features themselves are scaled to the same size. Because let's just imagine that for some reason one of these features here was tiny. So to get that to have any predictable quality, you will need to make that beta very large, right? Just to amplify it, to get it to a normal range. And so that doesn't necessarily mean that that feature is really important. It just means that it was small. So if you really want to look at the size, the absolute value of the beta hats, and see which one is most important, then you should make sure that you first scale all your features to have roughly the same size. We'll talk about this more later. As we saw in a homework problem for, I think, the last homework, when you're doing linear regression alone, there's really not any need to scale your data beforehand, to normalize it. But now that we start talking about feature selection, it is very important to normalize your data beforehand so that you can look at the coefficients and see which ones are more popular. And as we'll see, some of the techniques also require them to be scaled so they're roughly the same size. So hold that thought. We're going to talk about that in more detail later. But okay, so how do we do the fitting? Well, we know how to do this. We can import the linear model from sklearn. And in fact, last time we talked about doing stuff with for loops, where you do cross-validation with for loops. Well, not surprisingly, sklearn has all sorts of routines written to do that for you. So for example, there's this cross-val score where you can do all the cross-validation in one line of code. So you give it your model, linreg, which came out of when you instantiate it this way. You give it your training data. You give it one of these cross-validation objects. Or if you want, if you leave this out, I think it assumes tenfold cross-validation. I can't remember. And you tell it how exactly you want to evaluate the errors. So here we're going to use negative mean squared error. The reason why it's using negative mean squared error is just because it wants the scores to be small if something is actually large. If for a high score, you want something to be large, so you want to look at the negative mean squared error. So if that mean squared error is, is large, it's going to be a big negative number, which is small. So that's why we have the negative, just so among all the different score options that it gives you, that they're all large when it's good. Okay, so we do this, we compute our scores, and it actually gives you all the different scores from all the different test folds, and so we can just take their mean, we apply the negative here to get rid of this negative, and finally we get the mean squared error of cross-validation for our least squares estimator, which turns out to be 0.405. Okay, so the question is, for essentially this whole unit, can we do better by somehow choosing some subset of these features and using only the subset rather than using all of them? That's feature selection. Okay, any questions so far? Okay. So let's talk a little bit about feature selection. So as we just talked about a few minutes ago, the motivation is that we know from our bias variance trade-off that if you use too many features, too complex a model, you have a large error variance. So the idea is let's use fewer features. The problem now is it's not like polynomial regression where we might just remove the highest orders. We actually don't know which features to leave out to get fewer. So that gives us this feature selection problem. We want to somehow keep the best subset of D total features, but the whole question is how do we figure out that subset? And we said that the best thing to do, if you can afford it, is to use what's called exhaustive search. So you look at every possible subset out of the 2 to the D of them, and for each one of those, you run k-fold cross-validation. That's our go-to method. Again, that separates the training and test to make sure that your test doesn't depend on your training. So here, we can get some decent estimates of how good that subset of features will predict our targets. And we just choose the subset that gives us the smallest cross-validation error among all the possible subsets. Okay, so great idea, except in practice, this is often too expensive. So we need other ways to do it. So we're going to talk about 3 different ways: stepwise selection, correlation-based methods, regularization-based methods, such as lasso. And we're going to focus on the last one for most of the unit, but let's talk about some of these other ones first. Okay, so there's several ways to do what's called stepwise selection or stepwise regression. So forward selection is the first one, and this is the way it works. You first look at single feature models. So you say, what happens if I use feature 1 alone? What happens if I use feature 2 alone? What happens if I use feature 3 alone? You go through all D features, figure out which is the single best feature using cross-validation. Once you know which is the very best single feature, you keep that. You add it to your keep list. Then you keep that one, and now you say, I have D minus 1 features remaining. Which one should I add to my best feature to get the best pair? So now you go through D minus 1 possibilities. And finally, at the end of that, you have your best 2. Then you have D minus 2 left, and you go through them, and you add that one. Now you have your best 3, and so on. And if you think through it, this is on the order of D squared complexity rather than 2 to the power D, which is way smaller when D is big. Okay, so in fact, you don't even have to go all the way down to the max, or out all the way out to the maximum D, because what you'll see is as you add 1 feature, 2 features, 3 features, your RSS, your mean squared error, will get smaller and smaller, right? But eventually, when you have too many features, it will start to climb again. And at that point, you know you've gone too far. So you just keep adding features until things start to get worse, and then you back off, and you say, I'm going to stop where I was. Okay? So that's how we do forward selection. We start with an empty model. We gradually build it until things start getting worse again. Is that making sense? Okay. The other way we can do it is we can start with a full model, start with all D features, and you take one out. Figure out which is the best feature to take out. Once you figure that out, you throw it away, you never consider it again. Then you say, which is the next best feature to take out? Once you figure that, you throw that out, now you have, and so on. And eventually, once you take out too many features, your RSS will start to get worse, and you know I've gone too far, and you go back to the best situation you had, the best feature subset. So these are practical methods. They are not optimal because they're what we call greedy or myopic. It could be that you make a suboptimal decision at one stage, and once you've made that decision, you can never go back and include or disclude that variable. So that's the issue with them. They're not optimal. They often work well, but you can't claim that they're optimal. So very practical. And they are implemented in scikit-learn's recursive feature evaluation with cross-validation, RFECV. Okay.
So we decide on the basis of like group of values after processing all these things, like we should add more features or not.
Yeah, so these methods will, like forward selection starts with 1, then 2, and then eventually it gives you a subset that it thinks is best. And so the only point I want to make is it's not necessarily the best subset. If you considered all possible subsets, you may have found a better one, but it only is d squared complexity at worst to find this one, whereas the optimal one takes d2 to the power d complexity to search through them, which is much larger.
So while trading, we keep all these values in the cache, and then analyze that like at this point the values had decreased this much, and after that it has started to increase. So we just keep only those features till when the values decrease.
Yeah, but at every stage, we do cross-validation. Okay, so it's like I look at all single feature models. There's d total single feature models. And I use cross-validation on every one of them to find which is the best. And then I keep that single best feature, and I figure out of the remaining features, which should I add to it. I do cross-validation for every pair, and so on. So I do cross-validation at every stage, not at the end. Okay, any other questions? Okay, so these are pretty good, but there's other ways to do it. So another thing you might say as well, shouldn't we be looking at how correlated each feature is individually with the target? Maybe if I have a feature that is highly correlated with the target, that would be good for prediction. So what you could do is you could just look at every feature on its own, compute the, you probably want to use the covariance with the target. So this is our covariance, as we know, S sub y xj. So we're looking at the jth feature and our targets. We're computing that covariance. And maybe if it's negative, that's not a problem. So we really want to look at the absolute value of that. And so you could do this for all your features, and you could sort them. You could say this is the most correlated, next most correlated, and so on. And you could say, okay, now that I have them sorted in order from best to worst, now I have a model order selection problem. Should I use the first on my list, the first 2, the first 3, the first 4? And now we're back to the methods from the previous unit. So we sort first, and then we use model order selection. That's the idea. And I'm just presenting here one counterexample, which I already mentioned before, where this would fail, is if you have 2 identical features, maybe they're both highly correlated with the target, but because they're identical, they're redundant, we know that you shouldn't use both of them, but this method would sort them, and it would find them to be equally good, and it wouldn't tell you, probably wouldn't tell you to use one and not the other. Okay. So this is, again, suboptimal strategies. In practice, I find that these do not work as well, for example, as these are this stepwise regression, but it is an option. There's other things you can use besides correlation. There's all sorts of metrics that suggest how related 2 random variables are. So for example, there's something called mutual information that tells you how related 2 variables are. You don't need to know what it means. I'm just mentioning, it's just the name. There's other things like F value, P value, and so on. And these are all univariate statistics. What that means is you're just looking at, you're comparing the target to a single feature at a time. You're not looking at a subset of features together. You're just looking at one at a time. That's what makes these univariate. Okay, so in scikit-learn, you can use the select k-best function, and then you can choose between correlation, mutual information, F value, P value, whatever you want, and it will do all this stuff for you. Yeah.
What do you mean by how related
So it's kind of a vague concept. It means that somehow there's a statistical connection between them.
Aren't betas the representation of the relation between the feature and the meaning we're trying to find?
The betas are something specific that comes out of linear regression.
That's true, man, but in a rough sense, they are sort of a representation of the relation between a feature and the output.
They are one representation, but it's not the representation most people would come to if you said, I have two random variables, like how are they related? You probably wouldn't say, well, let me go fit a least squares model and tell you the coefficient. You could, but it's not what you do in most classes. Most classes, you look at things like covariance, mutual information, other metrics that people have developed to say these two variables are related in some mathematical way. But you're right. The betas give you an idea, but it's kind of a little bit of a not indirect way of doing it.
But here you're saying that if they're identical, you want to remove them, right? So how do you find that they're identical? Do you make any STC?
So one way to do it is if you also penalize correlations among your features, but then reward correlations with the target, that might be one way of getting around this issue.
So if there's high correlation between the features, then you would probably remove them.
Well, then you would choose maybe one and not both. Yeah. So there's all sorts of methods that have been proposed. There's probably hundreds of them that are of this family, that have been proposed over the years. But they're not what we're going to focus on. Just want you to be aware of them so that if somebody mentions them someday, you say, yeah, I heard about that. So we're going to focus on this regularization method, and we'll postpone until next time the discussion, but that's what we're going to focus on mainly. All right, see you guys on Wednesday.